Good afternoon, everyone. I'm Grace Gore from Georgia Tech, and today I will be presenting our paper, CausalVis, Visualizations for Causal Inference. When we think about causality, we are usually referring to how a certain treatment affects a particular outcome. Typically, when we hypothesize that two variables share a causal relationship, we would test our hypothesis by running an experiment, otherwise called a randomized controlled trial. However, not all hypotheses can be tested in this way. What happens when RCTs are infeasible? Consider this hypothesis. Does smoking cause lung cancer? For many good reasons, we cannot ask participants to smoke cigarettes and test if they develop lung cancer. In such situations, where RCTs are unethical, costly, or infeasible, we must rely on observational data, which brings us to causal inference. Causal inference is a statistical paradigm for quantifying causal effects using observational data. Consider again our hypothesis that smoking causes lung cancer. If we have access to observational datasets collected by hospitals or healthcare organizations, we can look at lung cancer rates in smokers and non-smokers. But simple comparison is not enough to establish a causal relationship. When working with observational data, additional steps must be taken to ensure that the estimated treatment effect is reliable and unbiased. In this example, age might be a confounding factor that affects both smoking and lung cancer. If smokers tend to be older than non-smokers, we can no longer conclude whether the change in cancer rates is caused by age or by smoking behavior. Identifying and adjusting for biasing variables, such as confounders, is crucial to causal inference. Only after adjustment can we then compare outcomes between the two groups to obtain the average treatment effect. The ATE quantifies the size of the effect of the treatment on the outcome variable and is often the main goal of causal inference. But as we have just demonstrated, causal inference is a complex process with multiple steps and challenges. So in order to better understand user tasks and to develop visualizations that support their work, we conducted a design study with 8 causal inference experts and researchers. After 2 rounds of interviews, we distilled the causal inference workflow into 3 main steps. Starting with observational data, the analysis begins with causal structure modeling, followed by cohort construction and refinement, and finally, treatment effect exploration. We also identify 8 user tasks, which informed the design of the 4 CausalVis visualization modules. I will next introduce the first 3 modules. For the last version history module, I'll refer everyone to the paper for more details. To better demonstrate CausalVis, I will be presenting in context of a usage scenario. In this scenario, we look at the UCI student performance dataset, which records student math grades and related data at 2 Portuguese schools. We are interested in estimating the effect of absences on grades. Here, absences is the treatment variable, and grades, or G1, is the outcome variable. We begin with the first step of causal structure modeling. Causal structure modeling is the process of identifying causal relationships between variables, typically represented using directed acyclic graphs, or DAGs. The goal of this step is to identify the right covariates, such as confounders, for statistical adjustment. Causal inference analysts would typically collaborate with domain experts at this step. For example, a teacher or an educator will be most qualified to identify factors that influence student absences or exam grades. But teachers and domain experts in general are often unfamiliar with causal inference and related terminology. So the causal inference experts in our study mentioned that they would like a tool to facilitate collaboration with domain experts. This led us to develop the DAG visualization module. In our scenario, we can pass the student dataset to the DAG module to manually create a DAG from scratch. Users can collaboratively add variables to the graph, position them, and edit the links between them. Once we have a DAG of causal relationships in our data, we can set the treatment and outcome variables. Here, we set absences as the treatment variable and G1 as the outcome variable. The DAG automatically updates to highlight the other variable types. From this, we can identify that there are 6 confounding variables and 4 prognostic variables that should be adjusted for. Together, these variables are called covariates. The next step of causal inference is cohort construction and refinement. In this step, we want to select our treatment and control samples from the observational dataset. In order for a cohort to yield a valid causal effect estimation, the distribution of the covariates between the treatment and control groups should be similar. There are different ways we can adjust for covariates. In this example, we will use the matching method. At a high level, the intuition behind matching is that given all samples in the dataset, for every individual in the treatment group, we match them to an individual from the control group with similar covariates. However, some samples may not have a well-matched counterpart. in which case we want to refine the matching algorithm to discard these samples. But how can we evaluate for covariate balance? That is to say, how can we evaluate the matching outcome? From the previous DAG creation step, we know what covariates need to be matched, but it would be difficult to evaluate each match manually by comparison. So one of the metrics we can use is the propensity score, which is the probability of each sample to be exposed to the treatment variable given its covariates. Since the propensity score is a summary of the covariate space, we can compare propensity score distributions between the treatment and control groups, and thus evaluate whether the groups are sufficiently similar. If we want to look at specific covariates, we can also compute the absolute standardized mean difference score, which quantifies the difference between a treatment and control group for a single covariate. Returning to our scenario, we used matching to select students from the UCI Student Performance dataset. We obtained a cohort with 200 samples. We then passed this cohort to the Cohort Evaluator module of the CausalVis package. The module visualizes propensity score distributions on the left and ASMD scores on the right. Here we see that the distributions of the treatment and control group propensity scores are similar. We also see from the ASMD plot that the adjusted ASMD values for all covariates are now below 0.1. This threshold is typically used to identify when variables have similar distributions. This is a well-balanced cohort, which we can now use in subsequent treatment effect estimation. The estimated ATE we obtain is 0.42. Students with frequent absences had slightly higher grades than students with few or no absences. But this is a very small difference and does not necessarily mean that either group is doing better than the other, which is also why causal inference analysts often want to know more than the ATE for the entire cohort. This brings us to the third and final step of treatment effect exploration, where analysts explore and compare subgroups in the dataset. Differences between subgroups indicate heterogeneous treatment effects. For our selected cohort, we calculate individual treatment effects, which are then passed to the Treatment Effect Explorer module. The distribution of individual treatment effects is visualized using a rain cloud plot. We see that the distribution is centered around 0, which matches the previously estimated ATE of 0.42. However, we can explore this dataset further. We can choose to group the cohort based on internet access and student health. Across the 4 subgroups, we can see immediately that students with poor health, who had no internet access at home, had a clear decrease in grades caused by frequent absences. Comparatively, this effect was less pronounced for the other subgroups. This is thus a heterogeneous treatment effect and may be an interesting finding for stakeholders in our scenario, such as parents or educators. Finally, causal inference analysts often repeat their analysis with different DAGs and cohorts. We developed the version history module to save the iterations, but I won't demonstrate the module here. I'll refer you to the paper and demo video for more details. We have now seen the CausalVis modules and how they correspond to the causal inference workflow. We then went on to evaluate the visualizations with 11 participants. Overall, participants felt that we addressed the 8 user tasks identified earlier. The detailed feedback is reported in our paper, and I won't reiterate it here. But I want to discuss a couple of interesting findings. Firstly, the iterative nature of causal inference means that analysts typically need to test multiple hypotheses. Our users appreciated how the interactive and modular implementation of the visualizations meant that they could repeat steps and refine their hypothesis really rapidly. A second interesting finding was that many participants valued how the visualizations helped them explain and communicate causal inference to collaborators. They also suggested adding annotations to further support this goal. In particular, some participants emphasized the importance of being able to tell a story about causality. In our paper, we discussed these and other findings in greater detail. Finally, we also learned some lessons from our design study about the importance of visualizations that complement instead of replacing existing workflows, how to prototype and design for computational environments such as JupyterLab, as well as the importance of working with diverse collaborators in order to understand different usage scenarios and tasks. This brings me to the end of my presentation. I would like to thank my co-authors, Ehud, Alex, and BC, as well as IBM Research and the GT Visualization Lab for their feedback and support.